Hi everyone, I hope you are okay. Our lecture today is about acid and base. And here as abstract, the Bronsted-Lowry definition, the acid as proton donor and the base proton acceptor. Proton, that meaning H+, okay, hydrogen without electron. We say the proton. And the Lewis definition, describe the acid as electron pair acceptor. يعني two electrons, electron pair acceptor, and the base electron pair donor. Okay, this the abstract for the subject. Okay, we will start with the Bronsted-Lowry acid and base. As we said before that, Bronsted-Lowry acid proton donor. Bronsted-Lowry base is a proton acceptor. A Bronsted-Lowry acid, look, the acid must contain a hydrogen atom, okay, because is proton donor, that meaning must be contain a hydrogen atom. This definition of acid and base familiar to the student because many inorganic acid like HCl, H2SO4, HF, all this they call inorganic acid. Are Bronsted-Lowry acid, okay, and the symbol for the Bronsted-Lowry acid is the Ha. Look, hydrogen A, that meaning substance has hydrogen atom. Here the Bronsted-Lowry base must be able to form a bond to a proton because the base is a proton acceptor. That meaning must be able to make a new bond with the coming proton to be stable. And the base must be contain available electron pair. Okay, we said before that to make a new bond we needed two electrons. That meaning the base of Bronsted-Lowry must be has electron pair, okay, and must be available or to be base. Okay, now this include lone pair or electron pair, the pi bond. Okay, the lone pair maybe it will be pi bond, it will be open as two electron to attack the proton, or maybe available lone pair is already exist on the atom and can be make a new bond with the proton. And here we will take examples. Look, the Bronsted-Lowry acid, all this is acid. Look, all this has hydrogen, HCl, H2SO4, H2O. H2O also can be work as acid or base. Okay, this is inorganic acid, and for the organic acid, the acetic acid and the citric acid. This is the structure for the citric acid. Okay, all of Bronsted-Lowry acid contain a proton. Look, all this compound has a proton. The net charge may be 0 or minus. Okay, look here, maybe 0 or plus or minus. Look, here is a plus, here 0, minus, negative, 0, 0, 0, 0, 0. That meaning the net charge may be 0 or plus or minus. The Bronsted-Lowry base, look to this base, the H2O has available in shape of electron. The NH3 base and shape of electron, OH minus, okay, full negative charge. That meaning is this very strong base, okay. Also NH2, this strong base. The acetone, because has an shape of electron on the oxygen, okay. Methylamine, also on shape of electron on the nitrogen, and the methoxide with negative charge, it will be strong, actually it will be strong base. And the ethylene, the pi bond here, the pi bond is also can be do as a base. And here he give you some the morphine is organic compound, as we can say there is acidic side here, the hydrogen, and we has basic side, and also here we has basic side. That meaning in the same compound is maybe there is maybe there is a acid part, also maybe there is a basic part. Reaction of Bronsted-Lowry acid and base. Okay, Bronsted-Lowry acid-base reaction, look, acid-base reaction result in transfer of proton. That meaning there is some side or some compound or some materials give a proton, and the other side, from the other side, there is some materials accept the proton. Okay, from an acid to base. That meaning we have transfer of proton from acid to base. This acid-base reaction also called proton transfer reaction. Okay, proton transfer reaction. Look to this reaction. The proton will be transferred from this to this. That meaning this is acid-base reaction or proton transfer reaction. And here are the examples. Again, he said the reaction of acid and base B. This the base. Look the base. There is a shape of electron. Okay, and the electron pair of the base form a new bond to the proton of an acid. This base make a new bond with this proton. Look, this base make a new bond. Okay, and here the proton in this acid, it will be this bond it will be broken, and the proton will be transferred to the base. Now the acid loss proton, it will be give you what? Conjugated base. The base accept proton, it will be conjugated acid. Okay, now why this conjugated base? Because has a shape of electron, can be do as a base. Why this conjugated acid? Because has a proton and can be do as acid. For this reason we said conjugated acid or conjugated base. Okay, this movement of electron in the reaction can be illustrated using curve arrow notation. That meaning we have to use the curve arrow notation to show how the electron pair it will be attack the proton, and the bond between oxygen and hydrogen it will be broken, and the two electron it will be converted to the oxygen atom. Then it is necessary to use the curve arrow notation. And for all the reaction, acid-base reaction, keep in mind the net charge must be the same. That meaning if you have negative here, and the other side also there is a negative charge. Okay, and that meaning the net charge it will be the same. Okay, and a double reaction arrow is used between starting material and the product. That meaning we use the double arrow for this reaction, because this reaction is equilibrium. That meaning the reaction can be give you the product, and the product maybe it will be come back to the starting material again. It will be reverse reaction. That meaning the reaction maybe it will be forward in this side, from the left to the right, or maybe from the right to the left again. Again, Bronsted-Lowry acid and base always result in transfer of a proton from acid to base. And here, take this example. What is the conjugated acid for this? That meaning this base now. What is the conjugated acid? Base take a proton, and it will be the conjugated acid. What is the conjugated base? Look, what is the conjugated base for this? That meaning this now acid. He said acid. Okay. That meaning what is the conjugated base? It will be acid proton donor. Okay, take a proton for this compound. It will be give you NH2 minus. Why minus? Because the nitrogen with 2 bond it will be minus, because there is excess for a shape of electron. And this homework for you. And in this example he said label the acid and base, and the conjugated acid and the base in the following reaction, and use the curve arrow notation. Now look to this reaction. If you look here, you will see the negative charge. The negative charge always it will be base, because a shape of electron. That meaning it will be do as the base. That meaning this is the base, and the H2O can be do as acid or base. If we have here base, that means the H2O here it will be acid. Okay, that means this shape of electron it will be attack the proton. it will be take the proton from the H2O, and this bond it will be broken to the oxygen to give you the OH minus. This is the OH minus, and here it will be the methane gas. And look to the answer here. The same thing. That meaning this is the base. It will be give you conjugated acid, and this is the acid. It will be give you the conjugated base, and this homework for you. And here in all proton transfer reaction, the electron-rich base donate an electron pair to the acid. Look, rich base. That meaning why rich? Because the base with a shape of electron with the minus. That meaning it will be high electron density. It will be electron rich, and which usually has a polar. The acid has a polar HA. That meaning the bond here it will be polar bond. That meaning we have partially positive charge with partially negative charge. Okay, and the hydrogen of the acid pairs a partial positive charge, making it electron deficient. That meaning the partial positive charge that it will be, we can say the electron deficient, يعني ناقص إلكترونية. Okay, here the electron rich species react with electron deficient ones. Okay, and here if you have two compound, and it will be entered to the acid base reaction, and how you know anyone it will be acid and anyone it will be base. Again, there is three important rules. The first one, common acid and base introduced in general chemistry will often be used in the same way in organic reaction. That means HCl and H2O are strong acid, and the OH minus strong base. When only one starting material contains a hydrogen, okay, it must be acid, because the acid is proton donor. If only one starting material has lone pair or pi bond, exactly it will be the base. Okay, a starting material with net positive charge is usually acid. Okay, a starting material with negative charge is usually the base. Keep in mind, memorize this please. This important for you, and this homework, and try to resolve homework. And here the acid strength and the pK. Okay, acid strength is the tendency of an acid to donate a proton. Okay, that meaning the acid faster give you the proton. Okay, that meaning it will be strong acid. The more readily a compound donate a proton, the more readily that meaning it will be stronger acid. Okay, acidity is measured by the equilibrium constant. When Bronsted-Lowry acid, the HA is dissolved in the water. That meaning we have acid dissolved in the water. Okay, what will be happened? It will be happened acid-base reaction, and the equilibrium constant, the K equilibrium, can be written as the following: concentration of the product on the concentration of the starting material. And because the concentration of the H2O is constant, that meaning we can write the K equilibrium in the Ka figure. That meaning the acid constant will be Ka, and equal to the K equilibrium, it will be concentration of the product on the concentration of the starting material. Okay, keep in mind that meaning if this strong acid, that meaning the concentration here on the product on the right side, it will be more than the concentration of the left side. That meaning it will be more than 1. Okay, more than 1. If they equal, it will be 1 to 1, the same concentration. For example, it will be 13 to 13. That meaning the result it will be 1. But here on the upper side, if we have high concentration, that meaning the K equilibrium will be more than 1, and here the acid it will be stronger. Okay, and he said how the magnitude of K are related to the acid strength. Stronger again, the stronger acid, the further equilibrium lines to the right. Look to the right, to the product, and the larger of Ka, the K equilibrium. And in the chemistry or in the analytical, we represent the Ka by the pKa. The pKa value, it will be minus logarithm Ka. Look, minus logarithm Ka. That meaning is the reverse for the Ka. That meaning if we have high Ka, that meaning it will be strong acid. But if we have less value for the pKa, it will be stronger acid. Okay, here the meaning here, because the Ka it will be minus logarithm Ka. Now take the Ka here, Ka value of typical organism 10 minus 5 and to the 10 to the minus 15 here. The larger number, okay, large Ka, it will be stronger acid. Small Ka, it will be weak acid. But here it will be reversed. The smaller number of the pKa, it will be stronger acid, and the large number for the pKa, it will be weaker acid. Again, the smaller of pKa, it meaning stronger acid. And here for further understanding, look to the acid, this HCl strong acid. Look to the pKa minus, and look to the methane gas. Look, 50, well, it is very large difference between the number here. That meaning this very weak acid and this strong acid. And the acid, when it will be react with the base, give you conjugated base. Look to the conjugated base, it will be weak. But for the methane gas, the conjugated base, it will be very strong and increase the basicity from the up to the down. But here increase the acidity from the down to the up. And look to the related pKa values for all this acid. Okay, take this example. Rank the following compound in order of increasing acidity, and then rank their conjugated bases in order of increased basicity. Okay, that meaning if you have this acid, anyone it will be stronger from the other. Okay, we will look to the HCl on the first, because the halogen is high electronegativity, and here the hydrogen chloride, it will be polar, and we have here partially positive charge. Okay, it will be stronger than this. That meaning it will be HCl in the first, and the second it will be acetic acid. Why the acetic acid also it will be stronger than this? This because the conjugated base here it will be stable. Okay, and there is a resonance structure here, and here it will be more acidic than the alkyne compound. Okay, here the double bond it will be can do the best more than the acid. Okay, for this it will be the weaker one, and here it will be the increased acidity. It will be like this figure, this number 1 and this number 2 and this number 3. Okay, if we write the conjugated base for the HCl, it will be Cl minus. The conjugated base for the acetic acid will be CH3COO minus. The conjugated base for this it will be CH2CH CH minus. Okay, anyone it will be stronger than this and this. Of course, this, because this is high electronegativity and it will be stable. And here there is carbon is normal electronegativity will be not stable. Also, we have negative charge on the double bond. It will be not stable. That meaning it will be increased basicity from right to the left. Okay, and this homework for we estimate the pKa of each of the indicated bond. Okay, that meaning any bond it will be has low pKa from the other. This and this and this. That meaning in the same way, anyone it will be more acidic than the other. The same thing. Okay, you have to think like that. Also, you have here another homework. Draw the product for each reaction. Okay, I want from you to draw the product and determine the direction of the equilibrium. Okay, the direction of the equilibrium. That meaning anyone it will be best the equilibrium to be from the starting to the product, or it will be from the product to the starting, and it will be preferred. أيها الأفضل. Okay, now Factors that determine acid strength. Okay, if we think about the acid strength, you have to think about 4 things. Okay, number 1, the element effect. Number 2, inductive effect. Number 3, the resonance effect. Number 4, the hybridization effect. No, anything that is stable the conjugated base, or anything that will be stabilize the conjugated base, make the conjugated base more stable, that meaning the starting acid, it will be more acidic. Okay, now in this slide, why the HCl here it will be a strong acid? Because the HCl, sorry, the Cl minus, the conjugated base for the HCl, it is stable. Why stable? Because high electronegativity. Okay, make the negative charge stable. That meaning the Cl minus can be kept, take the negative charge longer time than this. Okay, for this it will be the conjugated base, it will be stable. That meaning the HCl, it will be strong acid. Okay, now this 4 factor is so important to determine the acid to be strong or no. No matter which factor is discussed, the same procedure is always followed. Okay, now if I give you any compound, you have to think, or you have to apply in your mind all the 4th rule. Always draw the conjugated base. Always draw the conjugated base. Determine which conjugated base is more stable. Okay, now the more stable conjugated base, that meaning this acid, it will be more acidic. And I will give you here the explanation for all the rules. Now the element effect, okay, trained in the periodic table. It's dependent on the position of the element where is this in the periodic table. Number 1, again, the element effect. The most important factor that determines the acidity of the HA is the location of A in the periodic table. Okay, because in the periodic table we said the chemical properties is different from the elements on the left side in the periodic table and the elements on the right side in the periodic table. Okay. Now compare the element in the same row of the periodic table. Okay, now we will take some example. We'll take the acidity of the CH4 and the H2O. Now the H2O, this is the H2O. Write the conjugated base for the H2O. That meaning it will be remove 1 hydrogen, it will be give you H oxygen minus, and the methane, it will be give you CH3 minus. Okay, now anyone is more stable, this or this? Okay, of course the minus on the oxygen, because the oxygen is high electronegativity from the carbon. That meaning it will be here more stable, and this less stable. Okay, more stable conjugated base, it will be meaning stronger acid. For this reason the H2O, it will be strong acid from the methane. This is the element effect for the dependent on the position in the periodic table. Now as abstract, across a row of the periodic table, the acidity of HA increase as electronegativity of the atom, of the atom is increased. Okay, the electronegativity it will be increased. Okay, now this is more stronger than this. Why? Okay, look to the pKa. This is 3.2. Here the pKa 50. Why? Because the fluor is high electronegativity from the oxygen higher electronegativity than the nitrogen, and the nitrogen higher electronegativity than the carbon. And in the same column, compare the element down a column of a periodic table. Like the hydrogen, like the halogen, we have fluor, chlor, brom, iode. Okay, in the periodic table. Okay, then we will compare between this. Any element will be stronger than the other. In this case, to make comparing for the same column, now you have to keep in mind this. The size is more important than the electronegativity. Take the HF and the HBr. Okay, If we go for the electronegativity, the fluor is high electronegativity than the brom. In this case, you will be said the HF it will be more strong than this, than HBr. It will be stronger than HBr. But in the fact is reverse. The HBr is more or stronger acid than the HF, more acidic than the HF. Why? Because the size of the brom atom is more than the size of the fluor atom. Okay, that the size of the atom or the ion increase down of the column of the periodic table. So the Br minus is larger than the F, and here it will be negative charge. It will be stabilized in the big surface area. Okay, and the positive or the negative charge is stabilized when it is spread over a large volume. Okay, look to the fluor, small, and look to the brom, big. That meaning it will be larger anion. Here it will be small anion. For this reason, here it will be stronger acid than this. Okay, down to the column, the HI it will be stronger acid than the HF. And look to the pKa value -10, and here pKa 3.2. Small pKa value, that meaning it will be stronger acid. And here the example he said without reference to the pKa table. Decide which compound in each pair is the stronger acid. Okay, now anyone is stronger acid than this or this, and H2S or H2O. Okay, now for the answer, he said H2O and H both have the hydrogen. Yes, both have proton bonded to the second row element, because the acidity of HA increase across row of the periodic table. The HF it will be more acidic than the H2O. Okay, because the F on the right side of the periodic table and more than the oxygen, because the fluor is high electronegative more than the oxygen. For the H2 and H2 both have the both of them has the hydrogen atom bonded to the same elements, but here in the column the position will be up and to the down. Okay, because the acidity of HA increase down to the column of the periodic table, that meaning the HAs it will be more acidic than the hydrogen oxygen bond, and for this reason the H2S it will be stronger acid than the oxygen, again dependent on the size of the anion. Okay, here the sulfur anion is the size is bigger than the oxygen anion. Okay, and this homework for you, try to resolve this homework. The second effect is the inductive effect, and here is it will be during sigma bond. Okay, a second factor effect is the acidity is the presence of the electronegativity atom. That meaning in the same compound there is different if there is any excess electronegativity atom or no. Okay, to illustrate the phenomenon, compare ethanol and the 2,2-trifluoroethanol, this compound, and two different compounds containing OH group, the same group, OH from this side, OH from this side, and the pKa table. This the pKa is 12.4, this the pKa is 16, that meaning this less pKa, that meaning it will be stronger acid. Okay, from the pKa, and here because we are comparing the acidity of the OH group here, the same OH group bond to the compound. Okay, where is the difference between this and this here? Where is the difference? Okay, what causes the difference between the pKa or between the properties of the acidity? Okay, now here once again first draw both the conjugated acid and for both of them. Okay, this is the conjugated base for this acid and this is the conjugated base for this acid. And he said here anion it will be more stable. Okay, now we have negative charge on the oxygen, also we have negative charge on the oxygen. Now any negative charge or any anion, this or this, it will be more stable. Here's the question. Okay, both bases have the negative charge on the electronegative oxygen atom. Okay, but the second anion has 3 additional electronegativity fluorine atom. Here we have 3 high electronegativity atom. Okay, these fluorine atoms withdraw of the electron, take the electron density from the oxygen. Okay, that meaning this fluorine help the oxygen by withdrawing of the electron density. Okay, in this side, look to the arrow on this side. Okay, it will be withdrawing groups. Okay, and make the negative charge more stable. Okay, that meaning here we have small negative charge, but here we have here big negative charge. Okay, that meaning the inductive effect, it will be happen through the sigma bond. Okay, again the sigma bond. Okay, it will be happened during the sigma bond. This is the inductive effect. And an inductive effect is the pull the electron density through sigma bond caused by electronegative difference of the atoms. Okay, and here the same compound, like more electronegative and stabilize region of the high electron density, here the oxygen, by electron withdrawing inductive effect. Okay, that meaning this, the 3 fluorine stabilize the negative charge here by withdrawing the electron density from the oxygen to the fluorine atoms. Okay, also look to the red here is very light red, and here is deep red, that meaning this high electronegativity, and this small electronegativity, that meaning this is more stable than this. And the important thing, inductive effect result because an electronegative atom stabilize the negative charge on the conjugated base, the more electronegative atom, and the closer it to the side of the negative charge, that meaning the greater of the effect. Okay, now if when is the negative charge, or where is the high electronegative atom near from the negative charge, it will be the inductive effect, it will be stronger than the other. Okay, now which compound in each pair is high is stronger acid? A, B, C. Okay, we have here 3 examples. This it will be homework for you, and I want from you to decide that anyone will be more stronger acid than this. This or this, this or this, and this or this. Okay, please, I want from you to resolve this homework. The third one is the resonance effect. Okay, the resonance effect, a third factor that determines the acidity of the resonance. Okay, by the resonance. Okay, now we will take this, the ethanol and the acetic acid. Anyone it will be more stable than this. Here the question. Okay, look to the pKa. The pKa 4.8. Here the pKa it will be 16. Okay, of course in your exam I don't give you the pKa. I want from you to decide anyone it will be more acidic than another by the factor, by the inductive effect, by the resonance effect, by the hybridization. Okay, here I will give you, I want to draw the conjugated base. The first one, draw the conjugated base for both of them. Now here the conjugated base, also here the conjugated base. Now anyone is more stable, this is the conjugated base or this. Okay, here we have resonance. No, we don't have resonance. If you want to draw the resonance, we take the resonance before that. If you want to draw the resonance, there is no further resonance structure. But here, yes, we have additional resonance structure. This negative charge make the double bond, and the double bond it will be broken to make the negative charge here to be give you 2 resonance structure. Okay, here the difference in this 2 resonance structure make is the position of the pi bond and the lone pair. That meaning the negative charge here it will be disappear in this area. Okay, negative charge sometimes this oxygen, and the negative charge sometimes it will be on this oxygen. That meaning this it will be more stable than more resonance structure. It will be more stable anion. More resonance structure, it will be more stable anion. The negative charge here, it will be delocalized over the oxygen atom. Okay, delocalization of the electron density stabilize the acetate, stabilize the conjugated base, and make the acid it will be more acidic. Okay, here the idea. Again, resonance effect. If you have two compounds, one of them with resonance structure and the other without resonance structure, that meaning the compound with the resonance structure it will be more stable than the other, because the negative charge it will be disappeared over 2 or 3 additional atom like this. Look here, negative charge disappear on the 2 oxygen atom. That meaning the negative charge is now delocalization on the 2 oxygen atom. It will be more stable than this the conjugated base. For this reason, more stable conjugated base it will be stronger acid. Here. And again, resonance delocalization make the CH3CO minus more stable than the other conjugated for the ethanol, because the negative charge delocalization over 2 or 3 additional atom. Okay, here the homework for you. Try to solve this homework. And the fourth effect is the hybridization effect. Okay, hybridization effect is the percentage of the s orbital. Okay, now I will explain for you the final factor affecting of the acidity of the HA is the hybridization of A. Okay, to illustrate this phenomena, compare the ethane with the ethylene with the ethylene with the acetylene. For these 3 compounds, all of them containing CH bond. Okay, that meaning all of them has the hydrogen atom. Okay, if you look to the pKa, this has low pKa and this has the big pKa. Okay, low pKa, that meaning it will be stronger acid. Okay, why this stronger acid than this? Okay, the answer here, if you look if you look to the hybridization of the carbon here it will be sp3, and this carbon it will be sp2. Okay, and this carbon it will be sp. Okay, for this reason the higher percent s characteristic for the atoms it will be give you more stable conjugated base. Okay. Now the negative charge here on the sp carbon, that means this sp carbon has triple bond. That meaning the negative charge near from the high density electron. For this reason it will be more stable conjugated base. That meaning the acid will be stronger. Okay, here the negative charge on the sp3 carbon hydrazide. Okay, here the S characteristic is low than this. For this reason this it will be more acidic acid. Okay, increasing percentage of S character, increasing the stability. Okay, the stability and dependent on the stability. That meaning we have the position of the periodic table dependent on the stability, the resonance dependent on the stability, the hybridization dependent on the stability, the inductive effect dependent on the stability. Okay, that meaning all the factor dependent on the stability of the conjugated base and to give you a strong acid. Here the summary of the all 4 factor. It is this table can help you to memorize the fourth effect and how the effect make the acid stronger, make the stable for the conjugated base. Okay, this can helpful for you. And the Lewis acid and bases here. Now the Lewis acid and base. Again, the Lewis acid is an electron pair acceptor. Okay, the acid is electron pair acceptor, and the base is electron pair donor. That meaning here, example of Lewis base, this electron pair donor. Okay, electron pair donor. This it will be base, and this also electron pair donor, and this is also electron pair donor because the pi bond. Lewis bases are structurally the same of the Bronsted-Lowry base. Why? Because both of them has available and shape of electron, available electron pair. Okay, the lone pair are an electron pair or maybe in the pi bond again. The Bronsted-Lowry base always donate this electron pair to a proton, but in Lewis base, donate this electron pair to anything that electron deficient, not just the proton. Okay, and the Bronsted to the proton, but in the Lewis, no, to any electron, to anything electron deficient. Okay, any atom. Here the difference between the Lewis acid and the Bronsted acid.